Hello everyone, welcome back to my channel. So in this video we are going to learn about frequency division multiplexing. Frequency division multiplexing. In short, we will call it as FDM. Okay. If you are first time to my channel, please consider subscribing. So multiplexing. What is multiplexing? Multiplexing is the process of simultaneous transmission of two or more signals through the same channel. Okay, so if you have many signals to be transmitted like this, and you have only one channel which is to be passed from transmitter end to the receiver end. So this process where you have only single channel to pass many signals like M1 of T, first message signal, second message signal and third message signal, you want to pass all the message signal through the single channel, then that type of technique is called as multiplexing. Okay, so that type of technique is called multiplexing. And multiplexing, for analog communications we'll use frequency division multiplexing, and for a digital communication we'll use time division multiplexing. Okay, so in this we are discussing about analog communication technique, which is frequency division multiplexing. Okay, so multiplexing is the process of transmission of simultaneous transmission, that is all the signals are passed similarly at the same time, okay, through the same channel, right? So this process is called multiplexing. So channel bandwidth. Okay, so for transmission like this, what we need is channel bandwidth, and there will be another term which is called as signal bandwidth, which are both important because it depends on frequency here. So frequency in turn depends on bandwidth. So channel bandwidth and signal bandwidth are most important for defining this frequency division multiplexing. Okay, so channel bandwidth is defined as the range of frequencies the channel is capable of transmitting. The channel is capable of transmitting signals, without distortion. Okay, so the number of signals, okay, the range of frequencies means the range of frequency again depends on number of signals. So the number of signals the channel can be capable of transmitting like this. So it can transmit. If it can transmit 10, then it is okay. If it can transmit 15, then it is better. If it can transmit 20, then it is best. Okay, so that's how. So as the number of channels increases, if the channel bandwidth is more, it can transmit more number of signals through this. Okay, it can transmit more number of signals from transmitter to the receiver. So the frequency division multiplexing depends on two terms. One is signal bandwidth and second is channel bandwidth. Okay, a signal bandwidth, we know that signal bandwidth is the range of frequencies occupied by the signal. Range of frequencies occupied by the signal. by the signal. Okay, so signal bandwidth is the range of frequencies occupied by the signal. Range of frequencies occupied by the signal. Okay, so signal bandwidth is the range of frequencies occupied by the signal. By the signal. Okay, that is the highest frequency minus lowest frequencies, that forms the signal bandwidth. Okay, and channel bandwidth is transmitting the maximum number of signals. Okay, so without distortion, how many number of signals it can transmit is represented by channel bandwidth. So total number of signals added to each other, because when you are transmitting many number of signals, suppose if 20 signals are being transmitted and each are having a bandwidth of 5 kilohertz. Okay, so the minimum channel bandwidth required is 100 kilohertz. So minimum channel bandwidth required is 100 kilohertz. Practically, in this case, channel bandwidth must be greater than 100 kilohertz. Okay, so channel bandwidth must be greater than 100 kilohertz. That is, depending on the number of signals to be multiplexed, that is the frequency of the frequency of each signal being transmitted, the channel bandwidth must accommodate. Okay, so it should accommodate all the signals simultaneously. Okay, so for effective utilization of channel bandwidth, so for effective utilization of channel bandwidth, more number of signals must be multiplexed. More number of signals must be multiplexed. Okay, so if the channel bandwidth is suppose 100 kilohertz and each signal bandwidth, that is message signal bandwidth, is 5 kilohertz, and you are transmitting only 15 signals like this, so total bandwidth here, total bandwidth of the signals is only 75 kilohertz, and 25 kilohertz of the channel bandwidth is being wasted. Okay, so for effective utilization of channel bandwidth, more number of signals must be multiplexed. That is the thing here. Okay, so in this case 25 kilohertz of the bandwidth of the channel is being wasted because we are transmitting less number of signals than expected. Okay, so these are the basic points of frequency division multiplexing. Let me take another slide. I'll explain you more concepts. So next, this is the basic block diagram of frequency division multiplexing. Okay, so in this block diagram there are, suppose I am taking three signals to be multiplexed through the same channel. Okay, so if there is a communication between, that is if there is a connection, external connection between, physical connection between transmitter and receiver, then it is called as guided propagation. If there is no physical connection between transmitter and receiver, is called as unguided propagation. Okay, so guided means there is a physical connection like this, wired communication between transmitter and receiver. Okay, like coaxial cable. Okay, so all these are examples of guided communication, like transmission lines, waveguides. Okay, so transmission lines, waveguides, coaxial cable. So all these are examples of guided communication where physical relationship or physical connection between transmitter and receiver exists by the channel. Okay, so in unguided propagation we'll use antennas. Okay, so in unguided propagation we'll use antennas. There is no physical connection between transmitter and receiver, and in this case the free space serves as the medium. Okay, free space serves as the medium in this case, right? So we'll discuss these concepts later. Okay, so this is a frequency division multiplexing block diagram where you are going to transmit three message signals of same frequencies which are having same frequency range through the multiplexing, that is frequency division multiplexing. So these low pass filters are band limiting filters. Okay, so they are band limiting filters because normally for a given message signal there is no upper cutoff frequency. So in order to know the frequency of the message, we are passing it through a low pass filter which is called as band limiting filter, which limits the frequency. Let's say it will be some FM. Okay, so W is the highest frequency present in it, so that is the bandwidth of the message signal M1 of t. Similarly, W, the same message signal, the same bandwidth exists for M2 of t as well, and same bandwidth is also existing for M3 of t as well. Okay, so this is just an assumptions, because all the signals are of same type. If you assume all the signals are of either video signal or audio signal or any voice signal, so then bandwidth will be same. So W, W and W here. Okay, so how can we differentiate between the signals where you are having the same bandwidth? Okay, so up to here all the signals are having same bandwidth, but differentiation in the signals through the channel or at the receiver end is done by choosing different carrier frequencies. So here the carrier frequency is FC1, in the second modulator it is FC2, and in a third modulator if it is FC3. Okay, so that the output signal here, the output signal frequency from the first modulator is FC1 plus W, here FC2 plus W, and this is FC3 plus W, so that the signals are which are being transmitted from the transmitter are having different frequencies, even though the message signals are of same type, but using different carrier frequencies. Here FC1, FC2 and FC3, we are generating the signals of different frequencies so that they can be differentiated in the channel and also in the receiver end. Okay, so this is the process where you are adding where you are having different frequencies for different signals. Okay, so the same concept we are using for cable wire. So example is cable wire. So in the cable wire we are transmitting all video signals of different channels through the same cable wire only. Okay, so all the signals are video signals only, which are having same frequency, but using different carrier frequencies we can tune to different frequency range for the signal. Okay, so that is how we are differentiating them in the cable. Okay, so if you tune to some frequency which is FC1 plus W, that corresponding channel will appear in the TV. Okay, so that is the example here, cable wire. Right, so different frequencies are there, FC1 plus W, FC2 plus W and FC plus W. They are transmitted through the channel. And these band pass filters are tuned to the same carrier frequencies which we have used here in the receiving end, so that only corresponding signals will be received here. So the signal received here will be FC1 plus W, because this band pass filter is tuned to the frequency FC1, and the signal received here is the signal which contains the frequency FC2 plus W, and signal which contains FC3 plus W will be received by this band pass filter, and correspondingly its corresponding demodulator circuit is used, so that you will get the message signals at the receiving end. Original message signals can be used at the receiving end so that they can be given to any load. Okay, to given to any load, so that they can be displayed as pictures if it is video signal, or can be listened as an audio if it is audio signal. Okay, so this is the process which is going on in frequency division multiplexing. The point to be emphasized here is multiplexing is the process of simultaneous transmission. Here three message signals which are having same frequency are transmitting through the same channel, so that is called as multiplexing. Since this process involves depends on frequency, so it is called as frequency division multiplexing. So we are dividing the same message signals based on the carrier frequency. Okay, so based on the carrier frequency we are dividing the message signals, okay, which are having same frequency. So that is why that process is called as frequency division. So the frequency here used to divide is carrier frequency again. Okay, so frequency division multiplexing. Okay, so that is why this process is called as frequency division multiplexing. Got it? So this and different carrier frequencies are used, and then it is passed, because when you different carrier frequencies are used, it becomes different signals. They become even though they are similar up to here, but up then from here it will be of different frequency. So we can differentiate between those two between the three signals we can differentiate because of using different carrier frequencies. And band pass filters are used at the first stage of receiver circuit, okay, in order to get only the required frequencies, and then corresponding demodulators are used in order to get the message signals. Okay, so this is the process going on. So here two important points which you have to remember for this multiplexing concept is, for effective multiplexing, effective multiplexing means, what does it mean? To transmit more number of signals. If you transmit more number of signals, it will be effective multiplexing. Yes or no? So we can say that multiplexing is effective if you can transmit more number of signals. Okay, so to transmit more number of signals, there are two conditions. One is channel bandwidth. So this bandwidth of the channel bandwidth must be as high as possible. Channel bandwidth must be as high as possible. And second condition is signal bandwidth must be as low as possible. Okay, channel bandwidth must be as high as possible and signal bandwidth must be as low as possible. Then only we can multiplex more number of signals. Okay, so the number of signals, this is very important point, the number of signals that can be multiplexed, the number of signals that can be multiplexed is given by n. If the number of signals I am taking it as n is given by channel bandwidth by bandwidth of all signals, being multiplexed. Okay, so if n has to be more, that is number of signals that can be, so to transmit more number of signals, which implies effective multiplexing. For transmitting more number of signals, channel bandwidth must be as high as possible, because n is proportional to channel bandwidth. So that is the first point which I have written here. N, the channel bandwidth must be as high as possible, and bandwidth of the signal is inversely proportional, so bandwidth of the signal must be as low as possible. So for n to be increased, this should be very low and this should be very high. Okay, so if a channel bandwidth is more, you can transmit more number of signals. If signal bandwidth is less, then also you can transmit more number of signals through the same channel. Okay, so this is the basics of a frequency division multiplexing technique. Okay, so next the proper selection of the carrier frequencies are very important. FC3, FC1, FC2, FC3. So because the entire frequency division multiplexing concept depends on carrier division only. Okay, so we are dividing the carrier so that each and every message signal which are of same form, that is same message signals, are being differentiated by differentiating the carrier frequencies. Okay, so that is why proper selection of these carrier frequencies is most important. Okay, so how we have to select the carrier frequencies, or what is the condition for selection of carrier frequencies, is the concept here. Okay, so suppose if you have message signals like this. Okay, so different message signals are there. Sorry, so M1 of F is there. Okay, so message signals having frequency range same message m1 of f I am taking it as this. Suppose m2 of f I'll take different shape, but the frequency range is same, m, because it is different signal. So w I'm taking just to differentiate between all the three signals. Okay, I'm taking different shapes for better understanding only. Okay, so minus w to w, this is m3 of f. Then how will this is the spectrums of m1 of f, m2 of f, and m3 of f. So how will be the spectrum of multiplexed signal? The spectrum of multiplexed signal. Okay, so this is spectrum of multiplexed signal. Okay, so in this spectrum it should contain, it should consist all the frequency ranges. Okay, suppose if I am taking this as center frequency fc2, then okay, so this will be fc2 plus w. So I am taking, assuming all the signals as am. Okay, I am assuming all the signals as am because for easy understanding. So this will be fc plus fw, and this will be fc2 minus w. fc2 plus w, fc2 minus w, and the center frequency here I am taking it as fc3. So this will be fc3 plus w, and this will be fc3 minus w. And similarly, if you take fc1 as the center frequency here, so this will be fc1 plus w, this will be fc1 minus w. Okay, so as am signal, right? So why we have taken a gap here in the frequency range? Why we have taken a gap here? So this gap is called as guard band. Okay, so the frequency gap is called as guard band. Okay, so guard band is the frequency gap present between, is the frequency gap present between two signals in the spectrum. Okay, so when you draw the spectrum, the frequency gap present between two signals is called as guard band. So why this guard band is required? Because the practical filters does not have the sharp cutoff frequencies. Sharp cutoff frequencies is not possible. That means decreasing. So until fc2 minus w, there is some gain, and suddenly it cannot become 0. So suddenly it cannot drop like this. Okay, so even though theoretically we are drawing, but practically the sudden decrease of the frequency from, suppose the amplitude is 2 to 0, is this transition is not possible practically in practical filters. So it requires some frequency to be allowed to decrease its bandwidth or to decrease its gain from 2 to 0. Okay, so that is why in order to have that transition, practical filter gain decreases practically like this. So that is why there should be some frequency gap present between two signals. Okay, so that interference between two signals can be avoided. Okay, so to avoid the interference between two signals, we require some guard band to be present in between those two signals, right? So in order to have that guard band, what is the condition here is fc2. Suppose we are taking fc1 is less when compared to fc2 is less when compared to fc3. This is just an assumption. Okay, so for a better understanding of concept, I'm telling you this. So fc2 we have to take, it should be greater than fc1 plus 2w. fc1 plus 2w. Why? So this is fc1 here, and there will be the frequency, or the frequency gap here will be w, and the frequency gap here, or the frequency present here in this side band, okay, in this lower side band, and here upper side band is going to be W. And so that you have to choose this FC2, the relation between this FC1 and FC2. I am talking about the relation between FC1 and FC2. So FC2 should be taken by considering 2W, this here W and here also W, and there should be some guard band too. So that is why FC2 must be very much greater when compared to FC1 plus 2W. 2W why? So here upper side band and here lower side band is there in between FC1 and FC2. Okay, so that is why FC2 must be chosen like this. FC2 must be greater than FC1 plus 2W. Similarly, FC3 must be FC2 plus 2W. Okay, so if you select the frequencies like this, there will be no interference between the signals, and that can be easily obtained at the receiver end. So they can be easily demodulated and they can be obtained easily at the receiver end. Okay, so these are the considerations which you have to follow. So summarizing in short, I'll tell you important points once again. Multiplexing is the process of transmitting the many signals through the same channel like this. Okay, through the same channel you are going to transmit the signal, many message signals. So the process here involved is, even though the message signals are of same frequency, we are taking different carrier frequencies in order to make the signals different for the channel. To recognize them as different signals in the channel, we are taking different frequencies. That is why this concept is called as frequency division multiplexing, division of different frequencies, that is definition of different carrier frequencies for effective multiplexing. Okay, so thereby you can transmit the signals, and band pass filters are used to receive the corresponding signals only, and then corresponding demodulators can be used. These demodulators of different types. Suppose first modulator is of AM type, second is of DSBSC type, and third is of SSB type, and correspondingly you can use the demodulators. So this can be AM, this can be DSBSC modulator, which is a synchronous detector, and this can be SSB modulator, which is again a synchronous detector, and here you can use envelope detector, which is the most widely used detector for AM. Okay, corresponding demodulator can be used because based on different modulators you will have the corresponding demodulator schemes. Okay, that means you can multiplex not only same AM signals, but you can multiplex AM, DSBSC and SSB signals also. Okay, so then for efficient multiplexing, the bandwidth of the channel must be as high as possible. This is very important point, and bandwidth of the signal must be as low as possible. And number of signals being multiplexed is given by bandwidth of channel divided by bandwidth of signal. And these are the considerations which you have to follow for choosing this FC1, FC2 and FC3, that is carrier frequencies. Okay, so this is about frequency division multiplexing. Okay, so next we'll see one example on frequency division multiplexing, one simple problem. So in this problem he has given that 15 signals are each band limited to 10 kHz are transmitted through the same channel simultaneously after the process of modulation using FDM. So the guard band present between the signals is 4 kHz. Then determine the bandwidth of multiplexed signal if all the modulators are of type AM, all modulators are of type DSBSC, and all the modulators are of type SSB. Okay, so for this what we require to write is the number of signals being multiplexed is 15. Okay, and bandwidth of each signal being multiplexed is 10 kHz, that is bandwidth of each message signal is 10 kHz. Okay, so after passing each message signal through the low pass filter, which is called as band limiting filter, that is why it is called as band limited to frequency 10 kHz. Okay, so W is equal to 10 kHz, and they are passed through the frequency division by the channel using the process of frequency division multiplexing, and the guard band present is 4 kHz. Then determine the bandwidth of multiplexed signal. Okay, so what is bandwidth? So in the case of AM and DSBSC we will get the same result. Okay, so even though the modulators are different, but the result is same, because bandwidth of AM or DSBSC signal is twice the message signal bandwidth. Twice the message signal bandwidth is equal to 10 into 2, which is equal to 20 kilohertz. So bandwidth of each signal, okay, after the process of modulation, this is before the process of modulation. So after the process of modulation, the bandwidth required for each and every signal is 2W, which is equal to 20 kilohertz. Then these signals are passed through FDM. Okay, so these passed through channel using FDM. So bandwidth of the multiplexed signal, suppose if you have 15 signals like this, so 15 signals are there. Okay, so on up to 15 signals are there. So in between, how many guard bands will be present in between? So there will be guard bands, which is equal to totally 14 guard bands are present. Okay, between 15 signals, the number of guard bands is 14 in number. Okay, and the bandwidth of each signal, bandwidth of each AM signal is 20 kilohertz. 20 kilohertz here, 20 kilohertz here, and so on up to 20 kilohertz for all the 15 signals. For all the 15 signals, the bandwidth is going to be 20 kilohertz, and bandwidth of this guard band, that is guard band, is going to be number of guard bands is going to be 14, and each guard band is going to be 4 kilohertz. Okay, so total guard band in the multiplex, this is called as multiplexed signal spectrum. So total guard band present in the multiplexed signal spectrum is, total number is 14 and each guard band is 4. So 14 into 4 will make 96 kilohertz. Okay, so 96 kilohertz of guard band, and frequency of each message signal is 20. So that how many signals are there? Totally 15 signals are there. So bandwidth of multiplexed signal is equal to, so totally 15 signals are there, each having 20 kilohertz of bandwidth, 20 kilohertz. So I am writing for A and B, both solutions are same. So 15 plus 15 signals are there, each having the bandwidth of 20 kilohertz, plus in between them there are guard bands which are 14 in number, and they are, each guard band bandwidth is going to be 4 kilohertz. Okay, so this will be the bandwidth of total multiplexed signal. So this will be 300 kilohertz plus 96 kilohertz, which is equal to 396 kilohertz. This is the bandwidth of the multiplexed signal. Okay, so in the case of SSB, bandwidth of SSB signal is equal to the message signal bandwidth only. Okay, so this we have already discussed in the SSB concept. So bandwidth of SSB is equal to the message signal bandwidth only. So bandwidth of each signal is going to be now 10 kilohertz only. Instead of 20, it is now only 10 kilohertz. Okay, so here 10 kilohertz, bandwidth of this is 10 kilohertz, 10 kilohertz and 10 kilohertz. And guard band is same. Guard band does not have any change. Okay, so guard band is same, but only bandwidth of SSB is equal to the message signal bandwidth only. This changes. Therefore, in the case of SSB modulators, that is for C I am writing. So bandwidth of question C I am writing. So bandwidth of multiplexed signal is equal to 15 into, so now instead of 20 kilohertz, which is bandwidth of AM or DSBSC, now the bandwidth of each signal is only 10 kilohertz. 10 kilohertz plus 14 into 4 kilohertz. So 150 plus 96, which is equal to 246 kilohertz. Sorry. Okay, so this is how we can find the bandwidth of multiplexed signal. Okay.